Welcome back,
Hi.
everyone. Um, in the previous talk, we explored the strength of modeling for optimizing EPMA conditions. We will now continue with John Donovan, our next speaker. Hello, John, who will
Hey.
guide us through the quantification of beam-sensitive materials. Probably all of you know about John. However, I will try to share a few words about his background. John Donovan is the former director of the microanalytical facility at Camcor at the University of Oregon, and is currently president of Probe Software, a company specializing in EPMA acquisition, automation, and analysis software. He has over 35 years of experience in microanalysis with a strong focus on quantitative wavelength dispersive X-ray spectrometry. Throughout his career, he has made significant contributions to improving the accuracy and precision of X-ray microanalysis, including work on matrix corrections, spectral interferences, and beam-sensitive materials. He has received major awards, such as the MAS Award
All right, that's good. That's good. That's
and
good.
Presidential Science Award for his contributions to the field. So, John, thanks again for being with us, and
All
the
right.
floor is yours.
Thank you so much.
I will
Thank you so
stop
much for having me.
sharing my screen.
Yes.
All right, that's great.
Looks
Thank you so
good?
much, John.
Okay. So I'm gonna, yeah, so Aries talk introduced the topic of beam sensitivity in samples and why that is. And so we're going to talk mostly about how to deal with that. It's not getting any easier with FEG emission uh, instruments where you can focus the beam even more tightly. It's basically an issue of putting a lot of electrons in a small place. And so we're going to talk about that. I'm working on this project with Julian Law and Annette Vonderhand, and we should have a paper out this year. And but basically, what is the problem with these, what we used to call volatile, but now we refer to as time-dependent intensities, because there are a number of mechanisms that occur with this. And this has been known for many, many, many years. Actually, maybe this should be 35 years now. This is an old slide from John Furnell. But basically, it was observed pretty early on that over time, these intensities can change depending on the conditions and the elements involved and the materials that we're looking at. So a lot of papers published on this. As I mentioned, we're going to have a paper out this year that will go into this in some detail. But I think we've got a good handle on dealing with very sensitive samples now that we didn't have previously. And I'm going to talk about that. But first, let's, as Ari showed, there's basically a few productions from our electron solid interactions. We're going to be looking today at scattered electrons, which end up creating the heat that we're worried about, and then the emission of characteristic X-rays and how those are affected through either volatilization or ion migration or structural damage to the sample. So basically, we have an electron beam coming into the sample, and it deposits electrons into the material. And that, because electrons have both mass and charge, the mass will excite the structure and create heat, and the charge of the electron will create a subsurface charge. And that depends then whether some of these ions that are created, whether they are mobilized or not. And in the case of heat, and this is another thing that CalcSAF can do for you, you can put in the thermal conductivity and the beam conditions, and it will tell you, for example, that as you can see here, in aluminum metal, you only get maybe a 1 degree increase in temperature at 30 nanoamps and 15 kilovolts 1 micron, but in calcite or carbonate, you would get 43 degrees C, and in a mica, 306 degrees C. So you can see that it depends very much on the material, but also the beam conditions. Yeah, and the heat creates the ion mobility and lattice damage, and the subsurface charge creates the electric field potential. All right, so something that is, I'm not going to talk about very much, but there is an interesting effect just based on the structure of the material. Here's an SiO2 glass where I've analyzed some traverses here, and you can, in the reflected light, you can see where the beam was. But if you look at quartz, SiO2 quartz, the damage is much more apparent. And this has, people have looked at this, and if you want to learn more about it, you can. But basically, this is looking at absorbed current here. And you can see that the quartz is very affected in terms of the absorbed current. So something's going on, and you can find out more about this from this paper by Kezo. So the thing is, though, that's interesting, I think, is that the intensities of an element, in this case sodium, can decrease over time, but other elements, and this is because when the ions migrate, positive ions migrate further into the sample due to the subsurface charge, you can also have elements that do not migrate, but are maybe more held closely in the structure, and those will appear to increase over time, but it's mostly because we have less absorption from the elements that have migrated deeper. That's a very important thing. And this is not in the case of a typical kind of geological glass. That might be silicon and aluminum will increase over time, while sodium and potassium will decrease. Did I say that right? Silicon and aluminum will increase and sodium and potassium will decrease, apparently. And this, we think, is actually from ion mobility in many cases. Here you can see an example that Aries showed this same plot here. This is hydrogen, which actually is more really, I think, OH, and because it's a negative ion. In the case of the positive ions, like sodium and lithium and potassium, these are depleted in the surface areas, whereas the hydrogen is increased in the close to near surface. So that's an explanation for what we think is happening in many materials. This is kind of maybe the most beam-sensitive glass I have ever found. This is a NIST K375 glass, and it has a published value of 10.42 weight percent of sodium. So it's a very, very high sodium glass. And as you can see, the totals are not very good, nowhere near where they should be. And you can see we have a 60% error on the sodium, lower than it should be, and the silicon is about 4% higher than it should be. So if we do a correction, though, using these TDI corrections, you can see that we actually did pretty well here with the total. And you can see that we're now within about 1% accuracy on a material that has as you can see here, a 166% correction. So even in the case of an extremely sensitive material like this glass here, which was, I think, originally developed for storing nuclear waste, you can do a pretty good job. So how do we correct for this? Well, basically, if there was no time-dependent intensity effect, we would see a constant intensity as a function of time. But if there is a sensitivity effect, as you can see here, the intensity will either change, either decrease or increase over time. And what we're going to do here is we're going to really just calculate the slope of this effect and apply that slope to the intensities. And the reason for this is so that you can actually apply this slope correction to different intensities. So if you want to, and this is an option you can do in our software, you can either correct each acquisition for the TDI effect, excuse me, or you can assign a slope to a number of different points, and that way you will know whether the changes you're seeing are due to variation in the TDI correction or the actual material composition. So how do we do this? So this is really we're just doing a log natural fit here, and then of course you can correct this back to the linear intensity by exponentiating it. And then we can also do, for more extreme examples, we can do what I call a hyper-exponential fit, which is basically a quadratic fit in log space. And then for things get really crazy, you can do a double exponential, which is a log fit in log space. And this is, when you see something like that's this large an effect, you really have to start worrying about whether your extrapolation to 0 time is accurate. So here's kind of some data here, and this is looking at sodium, natural log as a function of time, and it looks like we're doing a pretty good fit here, but it turns out if you actually do a quadratic fit, we're actually maybe getting a bit more accurate extrapolation to 0 time, although as I mentioned, it's really a slope correction. But sometimes, you have a very beam sensitive glass like the one I showed you earlier, and then it's problematic whether you're extrapolating accurately. As this, slope becomes vertical, you're really guessing, how how accurate your correction is. So, but you can get too little a correction also. And that would be the case where you basically didn't have enough electrons, either through beam current or a sufficiently focused beam, that it takes a while for the sample to warm up. And so the ions aren't mobilized initially. And so this means that you try to extrapolate to 0 time, and you're going to be off a little bit. So this is what I would call a too cold analytical situation here. In this case, you can see we're at 15 kilovolts, 10 nanoamps, and with a 20 micron beam. So that's too easy. This, on the other hand, where you have 100 nanoamps and 5 micron beam, this is too hot. And so what you want to do is you want to have, maybe you could call it a Goldilocks situation, where you adjust it so you get enough mobilization to occur immediately, but it's not so much mobilization of the ions that you can't extrapolate accurately. So here is an example of an even more sensitive beam glass with about 14% sodium in it by weight. And you can see we're getting a TDI correction here of about 90%, which is still a lot, but you can see from the extrapolation here that we're doing pretty well. We're getting close to 100% total. And in this case, the silicon, we're able to extrapolate quite nicely. And you can see that we're getting decent results. So when you do have too much mobilization, you can get weird effects. And some of this is depending on crystallographic orientation. Some of this is as other structural kinds of problems. But if you're looking at a sample like this, which is fluorine I think in a apatite sample, that curve there is pretty difficult to model. So what you want to do is get back into a more linear regime, and where you can extrapolate or find the slope. And as I mentioned, there are crystal orientation effects. In this case, the Wilberforce apatite, which is a well-known material for standard for phosphorus and fluorine and other elements. Here we see no TDI effect as a function of time. And but in this orientation, we are seeing something. This is the same material, but a different grain that's oriented slightly differently. And in fact, if we fit this to a hyper-exponential, we get actually a better fit there. So this is something we need to keep in mind. So let's see, yes. And so this brings up the point, well, we need to run TDI on our unknowns, but maybe we need to also run it on our standards if our standards are also beam sensitive. And if they're crystallographically dependent on, in terms of the TDI effect, then maybe we need to run them on both. So practical consideration. So here's a kind of a screenshot from our software. And basically we can do you could do a self-calibration of TDI. You can also do an assigned calibration I mentioned earlier, where you just do a calibration sample and apply it to a number of samples, which might be useful for statistics. But in this one is kind of nice because it basically deals with whatever you have. And in this definition, you specify the number of sub-intervals. That is how many, you see, you're going to count for, say, 30 seconds. You might want to divide it into a number of 5-second intervals or whatever, 6-second intervals. And then also, as I mentioned previously, we might want to apply this TDI effect on our standards also. Then there's also the question of, what if I have, like, I want to measure, 10 elements or 15 elements? How do I deal with beam sensitivity for all those elements? And that is a good question. And what we've come up with is a method of doing TDI on multiple elements on the same spectrometer, because you wouldn't want to do the fluorine and phosphorus after the beam has been sitting there for whatever, a minute or more, however long you're counting, on the first elements. So we want to be able to do the TDI correction on all the elements. So how do we do that? So we can set up our first 4 elements or 5 elements here, do an acquisition on that. And then what we can do is we can set up a separate acquisition for 5 more elements. And if we want, we can set up a third acquisition with 5 more elements. And what we would do is we would measure each of these sets of elements with a small stage move in between. Now, of course, this assumes that the sample is homogeneous, but maybe that's something you can assume. And then what we will do is we will take those three samples and we will combine them and perform the matrix correction and the TDI correction all at once. Let me go back there. Sorry about that. So as you can see down here, here's the TDI correction applied to all 15 elements. Now, some of them it didn't really matter, but some of them it did. So this is worth considering. Some more things. Sometimes sodium doesn't decrease over time. Sometimes it increases over time. And this is a mortar material, a very unusual response. It has to do with the large amount of water present in the material. And sometimes you don't have a TDI effect. And if you apply a TDI correction, you'll actually get more scatter in your data. So don't apply the correction if you don't need to, would be my advice. Okay, so it's not just for major elements. It's also true for trace elements. And this is something that I think needs to be looked at more. We're going to be looking at it a little bit ourselves on our paper. But just keep in mind that it's not just major elements that can have TDI effects. All right. Okay, so Erie mentioned measuring water by difference. Just for fun, I tried to see if I could measure water by measuring oxygen, calculating the oxygen assigned to the cations, and then subtracting that away. And that's not easy to do. But I did measure in some synthetic glasses from Tony Withers. I measured a number of elements. And then, as you can see, the silica changing over time. You can see the oxygen changing over time. And then we decided to do a hyper-exponential fit. And we actually did okay. So you can see the FTIR data here. And that agrees pretty well with the H2O through measured excess oxygen. So you can do that, but it's a lot of work. I will tell you, it is a lot of work. So the other way to do it, which Ari discussed, was we can just subtract it from 100%. But there is a very important consideration, and that is we do not want to calculate this water by difference after the fact in our Excel spreadsheet. We have to do it during the matrix correction because that water has a fairly large, in certain circumstances, effect on the matrix. And so we're going to measure all our cations. We're going to calculate stoichiometric oxygen. We have to assume a stoichiometry for iron. If it's a mineral, we might be able to do that by charge balance. And then we subtract from 100. And what about CO2? So these are things that increase our uncertainty, but it's worth trying. And in fact, as I mentioned before, we want to perform these TDI corrections before the matrix correction, not after the matrix correction. And you'll see why in a moment. And there's our matrix correction, which is iterated. Okay, so matrix effects. Let's try this now. So let's not do any TDI correction and put in no water by difference. What do we get for our analysis? Well, we're getting about 95.3 weight percent total. And so we could say, well, that's about 4.7% water. Well, no, that's, as Erie mentioned, that's not the case. We're overestimating our water because we've underestimated our total. And so let's put in a TDI correction, but don't include the water by difference in the matrix correction. Now we have almost a 96% total. So that's about 4% water. So we went from 4.7 to 4% H2O. So that's better maybe, but let's do now the matrix correction for that. And now you see we're getting about we have 100% total, of course, because we're doing it by difference, but now we're getting 3.4% water. So we've gone from 4.7% water to 3.4% water just by doing the volatile correction and doing the water in the matrix correction. So let's see here. And then this is just an experiment we did to test these assumptions. And so we basically measured the gray points are without water by difference in the matrix correction, and the black points are after the correction for the matrix correction. And you can see the water contents lined up beautifully with the FTIR data. And so that's something to consider. And in fact, some labs that have this correction will have to report the water with the matrix correction for best accuracy, but also without water for comparing to other labs. And I would just say, don't be an other lab, be the lab that's doing it right. And by the way, it's not just the water that's affected, the silicon can be affected. Here, I'll give you an example. So without water in our calculation, we're getting about 70% silicon, SiO2. If we add the excess oxygen in, but without the hydrogen, we're getting 70.22 weight percent. With the hydrogen, we're getting 70.57. You'll notice that we had a larger effect just adding the hydrogen in. So yeah, you wouldn't think hydrogen would have that much of an effect, but it does. So include all the elements in your sample for the matrix correction, whether you measure the element or not. Okay. So now let's talk about that. All that I talked about so far was point analyses, spot analyses, but we can also map and correct for TDI effects. And so what you're seeing here is you have time 0, time 4, time, these are frames, these are replicate frames, maps, X-ray maps in time. And what you can do is for each of the phases in these materials, we can calculate on a pixel by pixel basis what the TDI effects are. And as you can see here, we might have very different TDI effects for an element depending on the material that it's in. And this is something that we should be looking at. So we require replicate X-ray maps, and we extrapolate pixel by pixel to 0 time. Okay, so we call this TDI scanning. And here's that 1718 nightmare material again, very high sodium. And you can see the sodium signal here. This is the raw signal of sodium intensities. We've got some kind of weird grid pattern there. Well, that's a complicated effect. We can discuss it later if you want. But the point is we can correct for that, even if the material is behaving in a very strange way. Here's the material corrected now for the TDI effects. And you can see we're getting about, 15% whatever of sodium. And in fact, that is actually the composition of this standard. Here's our acquisition. We've basically done 2.2 hours of replicate mapping, 1, 2, 3, 4, 5 replicate maps. And here is our results averaged out for the whole area. And we're getting the sodium certified value within 1 standard deviation. So not too bad. And the correction we're seeing there is quite large. The next here, I'll show a natural sample. This is a melt inclusion in quartz. And you can see we have our sodium here and our potassium there. Again, you're seeing this weird gridding pattern that's formed by the accumulated charge that is dragging along some alkali ions, we suspect. And then eventually at some point they become too many ions for the charge and they basically give up. The effect is variable, highly variable, depending on the scanning speed and the beam diameter and the thermal conductivity of the material and the, of course, alkaline ion mobility. Here's without a correction. If we don't do the correction, we just try to quantify. You see, we still see these artifacts in our melt inclusion here. And here's the potassium down here. So let's apply the correction. And what do we get? So here's the 5 frames that we acquired in time. And you'll notice that this material here, the sodium signal in this material is constant. It's not doesn't have a TDI effect. And so you can actually see the sodium intensity decrease over time here. And here you can see the TDI curves for a subset of pixels. And here at the bottom, you can see this is the sodium signal for our quartz matrix, which is essentially 0. And here is the sodium signal in our melt inclusion. And here with the correction, you can see we've pretty much removed the artifact that we had previously in both the sodium and potassium curves. And here is the degree of correction that we have, that we performed. Here we have about the sodium in this particular melt inclusion was about 100 to 200% correction for sodium. So a very large effect. This is not a map of intensities. This is a map of the correction. So this is how much we change the pixels, each pixel by. And in the quartz, you could see we essentially had close to zero change in the sodium intensity because, of course, there's no sodium in the quartz. And in the melt inclusion, you can see, though, we have about maybe 100 to 200% correction, depending on the pixel. And for potassium, we also see probably about a 10 to 20% correction. So that's kind of cool. And these plots are generated automatically, by the way, in our software. Oh, we can also do aggregate counting. Excuse me. So here's a single spectrometer looking at sulfur in, I believe, an otolith material. This is from a colleague of ours. And here we acquired the same signal, but in multiple spectrometers, and we've aggregated the intensities to get better precision. So why am I mentioning this for TDI? Because we know that some samples are very, very beam sensitive. This particular sample was very beam sensitive. And so it might be better to run a cooler condition and use more spectrometers to measure the signal we're interested in. And so we can improve precision on beam sensitivity, not just by counting longer, which might cause more damage, but instead measure our signal on multiple spectrometers. So in our paper that came out a few years ago, we discussed this, and I won't read this or give you much time. I will put this entire presentation on our user forum later today. And of course, there'll be a video that I'll post once Eunice has got that for us. But this paper is in 2021, and you may have missed it, but so take a look at it. But basically, it turns out that what we really want to do is we want to have a TDI correction to improve accuracy, and we might want to do some duplicate elements and aggregate them to improve sensitivity. So you can get accuracy and sensitivity at the same time, but you need to work a little bit at it. Okay, that's the forum there. I'm not, see, I don't have a whole bunch of time. Oh, I do, I have a little bit of time. Okay, let me talk about carbon. This is not something we usually think of as a volatile element, but carbon contamination is an effect that occurs as a function of time. And I will just like to point out here with this image, this is a reflected light image. A, a lot of manufacturers advertise a dry pump system to minimize carbon contamination, and that's not necessarily true. It depends on a lot of small details, including the maintenance of the instrument. But you can see that line there for the dry pumped EPMA, and you can just see the carbon track going right across it. So this is done in another lab. They sent me the sample, and we have an unusual instrument in that we have a cryogenically trapped sample chamber. And so, which is, even though we have a diffusion pump, which you think of as an oil system, our system is extremely clean. You can barely see the track right there. It's very hard to see, but that is looking at the carbon contamination on this metal. And so that's something to consider. On a stationary point, the carbon contamination shows some unusual effects. There's an initial increase and then an erosion over time. This was documented by Mike Matthews and Stuart Kearns and Ben Busey. And so that might be problematic in terms of that incubation period, or how Ben Busey likes to refer to it as decontamination time. He says we should start measuring our carbon signal after this initial increase there. Now, when we're scanning, as in the mapping or line scanning even, we will see a different effect. We will actually see the carbon increase slowly over time and build up. This is because we're spending a much shorter dwell time on each pixel of the sample. And so this becomes actually a much more predictable correction. And so here, after 8 hours of acquisition, you can see the carbon in this iron metal is quite reproducible. So this means we can correct for it. So this is without TDI scanning. You can see we're getting several percent carbon here. And if we apply the correction for the carbon signal, you can see we're getting close to zero, except for a few areas of contamination. So this is a doable thing. We can actually measure very small amounts of carbon now, if that is something of interest to somebody. This is another example looking at carbon, again, scanning. This is a line scan, and this is 10 replicate line scans. And then this is an analysis of without TDI here, as you can see. And then here we apply the TDI correction, and we do much better. And if you had a really clean sample, I think you could even do better than that. So the conclusions. Time-dependent intensity corrections are really important. They really can help give you an accurate quantification of even extremely beam-sensitive samples. You may need to play with the amount of beam current and your beam focus, but as long as you get into some kind of a response from the system that can be fit, then you can get a very good estimation of the intensity before the beam hit the sample. We also, again, as I just said, we want to optimize our beam conditions. Sorry. And we might need to not just assume a linear log prediction. We might want to use some more advanced fits to get better statistics and use smaller spot sizes because, we could decrease the beam current, but we lose sensitivity. And we could increase the beam size, but then we lose spatial resolution. So wouldn't it be nice if we could have both? So also, the TDI corrections must be performed prior to the matrix correction. You cannot do it afterwards. If you do it afterwards, you need to go back in and then recalculate the matrix correction and include all the elements, not just the analyzed elements, but the unanalyzed elements in the matrix correction. And apply these TDI corrections and methods to both the unknown, but also the standard materials if necessary, whether it's due to beam sensitive standards or orientation effects. And utilize these TDI corrections for both quantitative point analyses and quantitative pixel mapping. All right, and then I'm just going to put a plug here for, I mentioned this a little bit. There's a short course at the Microscopy and Microanalysis in 2026 in Milwaukee this summer, and it's going to be taught by some experts. I think it's going to be all day on Sunday, and I think it's going to be very interesting. And as you can see, we're going to cover a number of topics, and we, of course, will take lots of questions and discussion from the participants. So I do recommend that you join us there if you can. And I think it should be fun. So hopefully, see you in
It will
Milwaukee.
be on site, eh? The will,
Say again?
it will be on site, right?
Yeah, it'll be in Milwaukee. Yeah.
Okay.
Yeah, and I don't know if there'll be a recording of it. I'm not sure how that works, but yeah.
Okay. Thanks so much, John, for your talk. Very interesting, and I think we have plenty of time to answer a few questions. The first one from Myrto Simopoulou. She says that there is a high-pressure polymorph found in the melt veins of ordinary chondrites called albidic jadeite. Albidic jadeite is a supersilicic vacancy-rich pyroxene with excess silicon on octahedral site, actually. We have observed sometimes when taking an EPMA analysis with a 5-micron beam spot size that it is a beam sensitive, while in other samples we have observed that it's not beam sensitive. What do you believe affects that?
All right. Well, let me first say that I am not a geologist. So I only understood about half those words. But I will say that there could be a number of reasons. For instance, as I mentioned before, orientation. So some minerals are extremely sensitive in one orientation, but in a different orientation, they're not sensitive to these ion migration effects. Phyllosilicates would be one of the primary minerals, apatites. There's all kinds of things. I don't know about these particular minerals, but it could be from orientation effects. And it could just be how focused the beam is. Maybe, I always check that my beam is fully focused before I start a map, and then I defocus it to the amount that I want to. And on the Kamika instrument, that's required. In order to calibrate the focus, you need to focus and then defocus. And that's how it gets this linear distance there. Is that
Okay.
helpful? I
Mhm.
hope.
I don't know if, Annette, you want to add anything?
I just want to add, So occasionally, what I've also seen is that there can be an effect of grain size. And that is also a little bit touched upon in the papers of Cazot, where if you have very fine grain sizes, you can get more trapped charging. And I've sometimes seen also where you kind of get asymmetric TDI zoning, where I think it might relate to essentially of the thermal conductivity of the faces and specifically the adjacent faces, where again that's a rare thing, but where I feel like it matters a little bit if essentially I have a heat sink close by or not. And I mean, overall, what using TDI really showed me was that sometimes it's a little bit difficult to predict exactly when the behavior shows up. The crystallography aspect is usually very strong. And you don't always know what the crystallographic orientation is, but if you keep collecting data, sometimes you see behavior that is not explained just with crystallographic orientation. And so that can be one of the reasons why maybe there was sometimes an effect or not. And then another thing that I still don't fully understand, but what I've seen is when I would do titanium and quartz, which is very popular among the geologists, and so run high current analysis. Um, I mean, quartz is quartz, so I don't necessarily track the beam damage on the silicon, or I might as well, but I started also tracking the any kind of changes in the titanium signal because I saw that before with other trace elements, and there I do see it sometimes a difference between the data on the gas flow detectors versus the sealed detectors. And that cannot be explained with actual response from the sample, because that should be the same no matter what detector I use. And I chatted with a few people, and they also see that occasionally also on Kamika's. So there's something in the detector electronics that I don't quite know what's going on, but tracking TDI response has been at times eye-opening. And in the case with the gas flow detectors, there was like a 20% change. And I would have not known about it if I wouldn't have looked at it, just because titanium is not supposed to be beam sensitive.
That's
Uh,
interesting. Titanium, the signal was titanium you were looking at?
yeah, yeah. And again, it differs just based on the detector type. It can't be um, really a classic beam sensitive sample response. Owen sees it too on his
Yeah,
Kamika.
I mean,
So
I don't know. I mean, that's a really interesting observation. That might be worth looking into. I do know that, sometimes you get, like you said, various effects from having a more heat sink mineral nearby, that can reduce the heat. And of course, the Bristol lab, used a cryogenic stage for many years, to reduce that. And also, as you said, uh, the grain size it matters a lot, and there's I think with John Armstrong, Caltech, that if you take finely powdered glass materials, I mean you'll have all kinds of problems with having a finely powdered material as a sample, but you don't have any TDI effect because the ions won't cross the grain boundaries, which is interesting. So yeah.
One more question. Can TDI correction be applied when doing analysis combining EDS with WDS?
I mean, in principle, it could be. I haven't done it yet, but so we can acquire EDS elements with our WDS elements, but right now we don't acquire TDI on EDS because you'd have to acquire a full spectrum for every time interval, and then so it would be a bit of work. I've been asked about this before, and I've hesitated to get involved in it. But I mean, do any EDS manufacturers do a time-dependent acquisition? Do you know of any? Annette? Anybody? I don't. I've never heard of it. But, you know, I mean, in principle, yes, you could acquire EDF spectra in time intervals. You know, maybe
So,
Kaylee can.
Kaylee, if you want to.
To my knowledge, for quantitative analysis, there isn't. Some will have like a playback analysis for maps so that you can watch for beam damage while you're mapping and do a time correction there, but I don't know of any for quantitative analysis. It'd definitely be a good feature.
It's certainly something that could be done. Yeah.
Okay. Another question. What causes the anomalous increase in sodium intensity as opposed to the expected beam-induced migration?
I do not know. I mean, I expect it to have something to do with the large amounts of water present, or hydroxyl, and the hydroxyl, of course, is being a negative ion, would tend to be repelled from the subsurface charge, and so you'd collect a lot of hydroxyl near the surface, and maybe that increases the absorption. Well, no, wait a minute, that would. No, or maybe it decreases the absorption because you have to run the model. I would run the model. I don't know. There's certainly mortar is very high water content materials are interesting to analyze in the microprobe. You have any ideas, Annette, on that?
Sorry, I keep reading the questions and not listening.
Oh, no. We're just wondering, like, why when I analyzed, I showed a graph of the sodium signal.
Oh, the sodium migration. Yeah, no, I assume it might be very interesting to, I don't know, the resolution is tricky. If maybe some way with GM Raman, I don't know, to look at it. I mean, what I just get from all these things is that there's a lot of processes that we don't know quite about it. And as with everything, the moment you start looking more, you have the capability of looking more into detail. You find all these confusing
Very
behavior.
interesting research projects that can go on and on and on and on.
Yeah.
And so it was always a frustration for me when I was running the lab on a day-to-day basis, is that I'd find something unusual, or what's that, or that's cool, or what, some problem. And I'd love to spend, a week looking at it, but, on the other hand, you have a student, who needs data next week because AGU deadline,
But what I would say is also, I don't know, back when I was a student and also didn't always know what like factored into good analysis versus not, I would have much more outliers that needed removing because they had poor totals and whatnot. But now that I can track and correct data easier, there is like much less there's much less data spread. So in a lot of ways, okay, maybe we don't necessarily always know why, but there is in certain situations very good reasons to turn on something like TDI corrections,
Yeah,
and then
I mean,
you
the
can
nice thing about the
test.
self TDI correction, where you acquire a time intervals for every data point or every pixel, is that, maybe you don't need to use that information, but at least you have
Exactly.
the information, and you can look at it post-processing and say, oh, okay, so that was a beam sensitive sample or orientation or whatever. And then you have the data to make the correction. So you're all set. So, it does take slightly longer to acquire data this way because there's a slight overhead with the point analyses. You have to start a count and then start another count and start another count, start another count. But it's only a fraction of a second. So if you're counting, 5, 10, 15 seconds per interval, you can, it's a very small overhead. In the case of the mapping, the TDI scanning, yes, you have to acquire multiple replicates, but so normally where I would have done, say, for a quantitative analysis, I might have done, say, 1 second per pixel or 500 milliseconds per pixel, then just do 100 milliseconds per pixel and do it 5 times. And the acquisition is the same amount of time. So, we can do this, and it's quite informative, as you say.
Yep.
Okay. We have just 1 minute actually, and very quick question. Is sulfate a beam-sensitive material?
I would think so, yes. It's probably very beam sensitive. Yeah.
It is or can be, but I think in general it's like I'm not sure if it's always useful to approach a question like that, because I mean I would say almost everything can be beam sensitive if you go in brutal enough. I mean, if I analyze a garnet at 800 nanoamps with a focus beam, I would not be surprised if it eventually gets unhappy.
And some people
But
do. If you look at the
some people
diamond
do.
people, they will run a microamp.
So what I tend to do specifically as using TDI at times can have some time overhead is you can always test it. Just go on the sample at the conditions that you think you want to run it. Like if you have no idea and you don't have access to TDI corrections, the minimum that you can do is just like open your like put the beam on and observe the absorbed current. JOL has like a nice chart recorder in its system, but you can otherwise just look at it, and ideally you shouldn't see a relative change in observed current over the time of your analysis. And that is usually like the absorbed current tracks if you have compositional changes or if you have charging or something, and that gives you a good first order indication if maybe you need to widen the beam diameter or lower the current or something, like even without TDI tracking.
Yep.
Maybe there are conditions where you can be okay.
Yeah. First figure out if there's a problem and then deal with it.
Okay. So thank you, John, for your talk. It's always very informative, and I will stop this session now for 15 minutes until we be back for the next talk.